Yes, sir. We are live now. Please start.
Okay, good evening, everyone. Hope everything is fine at your end. So it's great that those of you who have followed the course, you made it so far. Hope you've been enjoying the course, doing all the assignments and learning along the way. So I just thought I'll maybe meet you one last time before you get ready for your final exams, which should hopefully happen later this month. So I suppose you would have had a chance to see the entire set of lectures by now. So you would have probably seen all the week 12 lectures as well, and hopefully you're also working out the problems for week 12, which should be due on Wednesday next week. And we have maybe a couple of weeks before the final exam. So if you have any questions on any of the assignments, I would suggest that you participate in the discussion board, put up your questions there and interact with us. And of course, if you do think we need another session, a live session where we need to discuss some specific concepts, I'm more than happy to do so. So can mention that also in the discussion forum. So I thought I'll use this opportunity to tell you a little bit about the final exam. I'm sure several of you are anxious about how the exam is going to be. And the key thing I want to mention is it's not going to be very different from what you've been doing in the assignments. The assignments, if you have noticed, you have about roughly 30% of the questions are conceptual multiple choice questions. 30% of the questions have been a little more like still conceptual, but a little more like true or false, match the following, reason, assertion, those type of questions. And then another 40% of the paper has been more of the quantitative types, where you may be even asked to design a sensor for a particular application and so on. So that's what you've been doing in all your assignments, and that's what you can expect as far as the final exam also is concerned. You will have roughly that 30-30-40 type of split in terms of the questions you can expect. So as long as you are comfortable with all the assignments that we have gone through so far, you should not have much of a problem dealing with the final exam. I'm not going to surprise you with anything there. So you may be, rest assured, just focus on solving all the assignment problems, focus on, learning or understanding some of the key concepts that we discussed as far as the course is concerned. And, you should be fine. So let me actually quickly go back and just give a very brief recap of what we have seen as far as the course is concerned. So let me first share my screen. Okay. So, you may remember that right at the beginning of the course, we were projecting what are the learning objectives of the course. And hopefully these objectives are making a little more sense now compared to what it was, at the beginning. So the first learning objective of the course is to identify different types of optical fiber sensors and determine their performance characteristics. So hopefully you can relate to this. By now, we looked at amplitude modulated sensors, phase modulated sensors, wavelength modulated sensors, and just the last week, we were looking at polarization modulated sensors. So we were analyzing what are the typical characteristics of these sensors, what are the concept behind realizing any of those sensors. and how to quantify each of their performance. So we took a lot of examples along the way. With the amplitude modulator sensors, we were looking at this example of absorption spectroscopy. We are also looking at the optical time domain reflectometer example. And similarly with phase modulator sensors, we were looking at optical coherence tomography. We looked at the hydrophone example, and of course, sorry, and also distributed acoustic sensing. We were trying to briefly look at what those concepts are. And then we went on to wavelength modulated sensors, and we were looking at fiber Bragg rating based sensors. We were looking at how to do the integration of fiber Bragg rating sensors. So that's what has been happening the past few weeks. And then, of course, we also look at the Bruon optical time domain sensors, so distributed strain or temperature sensing based on Bruon scattering in optical fibers. And last but not the least, we were looking at polarization modulated sensors. We were looking at the specific example of how to realize a fiber optic current sensor based on this polarization modulation principle. So hopefully, by now you can recognize any of these sensors, and you know how to determine their performance characteristics. But then this is a bigger goal. The bigger goal is to take a requirement from whoever. So if you are an engineer working for a company, your customers are requiring a particular solution, and then you take that requirement and then you say, I have all these type of sensors that I can do. Which of those is going to be best for a particular application, right? So that is actually a higher level thinking, in the sense that you are sort of inverting the problem and starting from the specifications of the sensor and then working backwards to see what would be an appropriate sensing solution for that particular problem. But hopefully you're able to do that. So we looked at some examples along the way. If we were given a certain requirement, how do you go about meeting that requirement? In the last couple of weeks, for example, we looked at the bridge monitoring requirement, the strain monitoring in bridges, and we broke it down into what it means in terms of the actual sensing technology that we choose for that application and how we meet that requirement. And of course, the final part is to realize and implement an optimal sensing solution for a given requirement, which is actually here it's conceptual, but then here it's actually implementing that. And of course, we also looked at what would be the implementation challenges when we pick a solution and then we try to realize it. There are a lot of practical issues involved, and trying to figure those out is actually a key aspect as far as any engineering problem is concerned. And some of these, you may be able to appreciate only when you actually go to the field and realize it. So we are unfortunately not giving you an opportunity to do that as far as this course is concerned. There's not a lot of hands-on skills that we are actually imparting, but nevertheless, I know some of you are doing research in this area, and you've been in parallel doing some related work, and you've been asking me questions on that as well. So, I am trying to support you as much as possible with those questions. So overall, this is the last thing that I had mentioned as far as the course is concerned. How to pick the right sensing technologies could be quite tricky, but you can possibly break it down into the requirement, whether it's a point sensing requirement or a distributed sensing requirement, whether it's a static requirement or a dynamic requirement. Is your perturbation, you know, it's going to be static, or whether it's going to be changing with respect to time. And if it is changing with respect to time, what is the frequency at which you expect things to change? And say if you have something that is changing at 100 hertz, then you can appropriately design your receiver so that it's limiting the response to a few hundred hertz and not picking up noise unnecessarily. And then, of course, it also matters as to what is the quantity to be measured, that is strain, temperature, force, pressure, rotation, and so on. For example, if it's rotation, then the immediate thing that springs to your mind is effect. And so you can essentially say that, okay, that's going to be based on a phase modulated sensor principle, where you're using a Sagnac interferometer. If it's actually a field measurement, an electric or a magnetic field measurement, maybe a polarization modulated sensor would be very good for that sort of an application, and so on. So it all comes down to what is the cost versus performance if you are realizing the sensor for a practical application. And the performance is already defined by the user. So that's actually given to you. So then your challenge is to implement that solution. First of all, find out what would be the optimal solution and implement that solution with the lowest cost. And when you talk about cost, an amplitude modulated sensor would be very straightforward because you don't need any demodulation there. So it may be a relatively simple solution, so it's not incurring a lot of cost. Whereas if it's phase or polarization, that could involve demodulation, and you have to be very careful about not picking up some stray environmental perturbations and so on, so that that extra features that to protect your measurement from these environmental variations may make the solution a bit more complex and a bit more expensive as well. And of course, when you talk about performance, we have seen several examples where phase or polarization modulated sensor is extremely sensitive. So you can get very high sensitivity, provided you have taken care of all the issues with the environmental changes. Whereas, if you're looking at amplitude modulation, maybe the sensitivity is not so great. So essentially, what I'm hopefully, leaving you with is knowledge of how to break down a particular problem, and then try to find appropriate solution from that. Okay, so that's. Those are the kind of things that I wanted to give a wider perspective about the course. But let me just go back and talk about some specifics, including some of the questions that you have asked already. But before I go to the questions, let me first, once again, share my screen. But this time I will share this dashboard. So this is sort of the overall performance that you've been able to put out as far as this course is concerned. These are sort of the averages that you have seen, that you have done over the over the entire course up to week 11. Week 12 is what you're doing right now. Overall, I should say I'm quite happy the past few weeks. Of course, week 10 could have been better, but then given that there is typically a sort of wearing out, your stamina is sort of, your intellectual stamina is under question when you go to the 10th or 11th week. So given all that, this is probably somewhat understandable. I was quite happy in week 9 that you were able to do very well. 78% on the average is a very good score. So hopefully with that sort of backing, you are feeling confident about taking up the final exam. I've already given you some tips about how the final exam is going to be, and if you can replicate this performance in the final exam, I'm sure that will be very good. Okay, so that is one thing I wanted to check, and the other thing is in the discussion forum there has been some questions which I have hopefully I've tried to answer those questions on the same day. Please keep them coming. Of course, one thing that I am not able to do is address this sort of a request. Please provide the notes of lectures. Unfortunately, this is the first time this course is being offered, and the transcripts for the course actually were released only a few weeks ago. And since then, I've been taking the help of TAs to go through the transcripts and also prepare the notes, but it's a very slow process. So we've not really been able to get very far. And of course, the transcripts that are available today is only up to week 7. So the remaining transcripts are yet to be done. So given all of that, the best we think we can do is before your final exam, make the verbatim transcripts available to you of all the transcripts that have been made available to us. So we are in the process of just focusing on making the verbatim transcripts available. Mind you, this is not like the notes that you would have for the course. So these are just verbatim transcripts of the lectures. But given the circumstances, I think that's the best we can do. Okay. So with that, let me move on to the next thing in the agenda, which is in terms of answering some of your questions. So let me look at the questions that have been already put out. So this is a question from one person who's basically saying, based on the material that have been taught in the course, they've been able to develop a fiber Bragg grating solution to monitor the temperature profile across a solar cell. That's very interesting, and apparently they've been able to successfully complete that work. And the next work that they want to take up is actually monitoring the fetal heart rate using fiber Bragg grating sensors. And the question is that there are very few references in this work, and what the thing is, what do I think about that application, and what exactly can be done? Well, so there are certainly challenges. One of the reasons that there are very few references as far as this work is concerned is because of the fact that when you implement a solution, fiber Bragg grating based strain monitoring system is actually a fairly straightforward concept when we are looking at it from a theoretical perspective, but then when you want to implement that in a practical manner, that can be quite in this case, we are talking about monitoring not a civil structure, which is relatively easy to monitor, but in this case, we are talking about monitoring the human body itself. So implementing a sensor on the body in sort of a non-invasive way, and in sort of, or at least in a minimally invasive way, and try not to disturb the function of the human body itself. And that can be quite tricky, especially when you talk about fetal heart rate monitoring, because now we are talking about a pregnant woman and trying to put a sensor on that body and then try to pick up the heart rate, which is basically acoustic emissions from the womb. And there the issues are that when we try to put a fiber brag grating, it has to stick on the body and also make a fairly good interface wherein any pressure variations from the womb can be transmitted through that amniotic liquid, and then it has to go across the body itself before we can pick it up from the surface, from the skin surface, right? So it is one thing to say, if we go back to, let me just share my screen once again. If we go back to the concepts involved in this, like what we talked about with the fiber brag grating sensor, we are saying that we are incorporating a fiber brag grating on the body, and then the perturbations, in this case, the pressure variations that come across, and then that is essentially stretching or compressing the grating, and corresponding wavelength variations, we have to pick it up, right? So this side, the integration can be a little challenging, but then again, I think in this sort of a situation where we expect perturbation changes, they are dynamic perturbations, but the perturbation changes are in the order of just a few hertz. We're talking about 100, 150 beats per minute type of numbers. So we're just looking at a few hertz change in the perturbation. So that is actually not a major challenge. You can use a spectrometer possibly to pick that up. But the challenge is how to effectively transduce the pressure variations here to the changes in the material here, changes in the effective index of the fiber brag grating, and that depends on what are the interfaces between the fiber and the source of the pressure variations, and how much are the pressure variations dampened by those interfaces. That determines the sensitivity of this system now. It is not so much limited by the sensitivity of the instrument, but it's limited by how the grating is applied. So in this case, I would say the biggest challenge is how to effectively incorporate the grating on the body, right? And so that I think is a challenge that not a lot of people have been very successful in achieving. So maybe that's one reason why there have not been as many publications in this. But that's what I would worry about. How do you package the sensor, and how do you implement it on the human body. I think that's where the key challenges are. Hopefully that address the question. So I'll move on to the next question. So the next one is about using, developing a fiber optic based humidity sensor for monitoring the sewage or how well sewage is treated in a actual plant. And for that, what this person is saying is that they are actually incorporating some polyamide at the end of a fiber, and in fact, they're creating a fiber fabric cavity at the end of the material and coat it with this agar material, which is sensitive to humidity changes. So the question is, how well we are going to be able to pick up changes in humidity through this. And the answer to that is, once again, how well are the optical fields in the cavity at the end of the fiber. Hopefully you know how to make that cavity at the end of the fiber, but assuming you know how to make that, the question is how well that cavity is going to be interfaced with the external medium. So in this case, you have an agar coating at the fiber end, but then the thing is, what are the fields, what are the optical fields that are existing at the end of the fiber? So you do need some evanescent field to be able to interact with the external medium, so that if there are any refractive index changes, that's what you're trying to measure. When the humidity changes, the agar material essentially changes its properties, optical properties, and that changes the refractive index of the coating. And when it changes the refractive index of the coating, if the field inside that cavity is interacting with the external changes, then it changes the effective index of the cavity, and through that you will see that the resonances, or what is called the longitudinal modes of the cavity, those are the free spectral range corresponding to the longitudinal modes of the cavity. And free spectral range is going to change, and so you would have to have a corresponding mechanism which looks at the change in the free spectral range itself. Okay, so so there's certainly a challenge with respect to how well the optical fields in the cavity are interacting with the agar coating, and so those are some specifics which I can probably take it offline and discuss with you. But from a perspective of this making this sensor, it's a question of how well the fields are interacting with the external medium. So the next question is about how to implement fractional order filters for noise reduction in FPG spectrum. So the question to me is not very clear. So when we talk about noise reduction in fiber Bragg rating spectrum, we need to understand what are the sources of noise. So clearly, whatever fluctuations in the intensity is not going to be a major source of noise as far as the FVG sensor is concerned, because what we are primarily interested in is the change in the spectrum, right? The change in the wavelength, the Bragg wavelength. That's what we are trying to pick up. So already, you have a reasonable what you say protection with respect to the conventional noise sources like thermal noise, short noise, receiver, and so on. So there is not as much of a problem, but the question is whether there could be some post-processing implemented in terms of fractional order filters for noise reduction. And I would say, yes, potentially the resolution, the sensing resolution can be improved by looking at these post-processing. But you know, even conventional filters like say Savitsky-Golay type of filters, those are good enough for such an application. And I don't think you gain so much more advantage by going to what's been called as a fractional order filter or Caputo filter. Okay, so that's all I have to say about that question. Now, there's one more question. Can we use the side lobes of the fiber Bragg grating for sensing application? So that's actually a very nice thought. So let me just go back and share my screen again. So we were talking about the spectrum of fiber Bragg grating. I think we were specifically talking about having a spectrum where there is a main peak corresponding to the fiber, corresponding to the Bragg wavelength, but then there are these side lobes. And I think during the lectures, I was talking about this process of apatization through which you can actually kill the side lobes. Now, the question is, it's a very interesting question. Can we use the side lobes themselves for sensing something? And for that, I think you need to understand where the side lobes are coming from. The side lobes are primarily coming from the fact that your average refractive index, you know, if it is sort of like a square change as shown in this blue line, then you have these side lobes. So that's the source of the side lobes. Now, can this be used for sensing? Possibly, although it's not conventional. You can possibly say that because of your perturbation, the average refractive index across the grating, that is actually changing its distribution. It's instead of being a square shape, because of the perturbation, it is becoming more like a Gaussian shape or some sinusoidal shape or something like that. If there is a change in the average refractive index like that, then the level of the side lobe will change. Okay, and that can actually change the that can be used for a sensing application. The other possibility is the position of the side lobe is determined by the period as well as the length of this interaction, length of the grating. So if there is some some external perturbation wherein the grating length is actually impacted, or say part of the grating is actually immersed in a liquid and the other part is in air or something like that, then the resonance corresponding to the part where the grating is in the liquid is different from the resonance that you have from air. So because of that, the period at which the Bragg wavelength corresponding to this region is different from this region. And that actually can also impact the side lobes, the strength of the side lobes as well as the position. So like I said, it's a very interesting thought, but you need to also ask the question, what is that you're not able to sense by just checking the change in Bragg wavelength itself? that you have to go to the side lobes, right? So I would think most of the applications you can just pick up whatever you want to sense by looking at the shift in the Bragg wavelength itself. And if that's the case, then you don't really need to go to the side lobes. But nevertheless, thanks for the question. It certainly got me thinking about where it could be useful. Okay, so now those are the questions that have been sent to me, or people have actually filled out the whatever form we had sent, the NPTEL folks had sent. So thanks for that. Now let me look at if there are any other questions here. I don't see any other questions as far as the chat box is concerned. So perhaps that's all we have for now. And so if that's the case, I'm happy to end the session right here. I just wanted to give you this thought once again that, as far as your final exam is concerned, please do go back and review all your assignments. If there are, questions where you do not understand how the solution has been worked out, please bring that up for discussion, and we are more than happy to clarify those. And of course, if not, good luck with the final exam, and all the very best.